Topic 9.2, single slit diffraction. Make sure you have your notebook and your data booklet available. And on page 9 of the data booklet, topic 9.2, we have just this one equation, theta equals lambda over b, where lambda is the angle in radians, in rads, between the central maximum and the first minimum, between central max and first minimum. This is of a single slit diffraction pattern. Lambda is the wavelength of light, and b is the width of the slit. Okay, so what is diffraction? Well, it occurs when a wave meets a hole in a wall or some screen that is of comparable size to its wavelength. The hole needs to be around the same size of the wavelength, so the wave will bend through a process called diffraction. So here we have a wave incident on an opening, and as it passes through the opening, the wave gets diffracted. If the aperture, or the opening, is much larger than the wavelength, diffraction will be minimal to non-existent. Note that some of the wave does get reflected at the boundary. So diffraction is caused by objects within the medium that interact with the wave. It is not caused by two different mediums in their boundary. Christian Huygens, Dutch physicist, explained the behavior of diffraction through his famous principle. Every point on a wavefront emits a spherical wavelet of the same velocity and wavelength as the original wave. So even though it's easy to draw the wavefronts approaching the aperture like they're all cohesive, the truth is it's every point on the wave that carries that information of the total wave. So in the case of light, you have a bunch of photons, and they go through this opening, and each individual photon has the same wavelength and velocity as the total beam of light. Okay, and so as these photons go through the opening, they all have the same wavelength and velocity, and they all kind of carry this information of the original beam. And this is what you see with this spreading out. And that is the diffraction. So the reason waves can turn corners is that the incoming wave transmits a disturbance by causing the medium to vibrate. And wherever the medium vibrates, it becomes the center of a new wavefront as illustrated below. But of course, light needs no medium. But here we'll use water waves. You can see the effect of aperture size on this bending of the wavefront. So it is each particle transmitting that information that contributes to this bending effect. Note that, again, the smaller the aperture, the more pronounced the diffraction effect. Alright, so maybe you remember path difference from topic 4, but if not, we're going over it again. So this animation will show two coherent wave sources. Coherent waves have a constant phase difference between them, and they have the same frequency. So we have two sources, S1, S2, and these will show the following, where you have a whole integer multiple of the wavelength between them. This is the condition for constructive interference at some distance away. So we have two sources of waves, S1, S2, and they're emitting waves, and these waves spread out. Notice that the distance between concentric circles for green and for the pink, that represents the wavelength. And we have this position here, P1, and the distance from S1 to P1, this point away from the source S1 is labeled as shown. And we have the distance between source 2 and P1 labeled as shown. And we can count the number of wavelengths between S1 and P1 and between S2 and P2. So that's 1, 2, 3, 4 wavelengths of distance between S1 and P1. And for S2 and P2, we have 1, 2 wavelengths of distance between S2 and P1. So the path difference between those is 4 times lambda minus 2 times lambda equals n times lambda. 4 lambda minus 2 lambda equals n lambda. So the lambdas cancel. That's a whole integer multiple in the path difference between the two sources. That's a place, P1, you would see a bright spot, a combination of both waves there. And that is, again, the condition for constructive interference. The same thing here between these two spots. Now again, for destructive interference, this is the condition. You have a path difference between the two sources of waves, and if that's equal to some whole integer plus a half multiple of lambda, the waves cancel. They meet out of phase. So here we go, source 1, source 2. Waves spread out, and we have this point here, P2. So the distance between S1 and P2 is 3 times the wavelength, and the distance between S2 and P2 is 2.5 times the wavelength. So this would be a position of destructive interference. 3 times lambda minus 2.5 lambda. That's a path difference of 0.5 lambda. N is 0.5 in this case. So you would see either a dark spot or a flat line. There wouldn't be any wavefront in that position. It's just another quick example. But that is the condition for destructive interference. So indeed, Huygens wavelets not only allow the waves to turn corners or diffract, they allow it allows for the wavelets to interfere with each other. So here we go, a series of waves, and all along the front are these wavelets. Places where you have, oh, these colors aren't matched up. Okay, that's fine. You'll have constructive interference where a crest meets a crest or a trough meets a trough, and destructive interference where a crest meets a trough. Here we can see the pattern as the wavelets spread out, and what you get if you could project these two sources of waves through an aperture onto a screen is this sort of intensity pattern that we saw last year. You would have the highest intensity of light in the middle. You would have places where the intensity went to 0 and places where you'd have subsequent bright spots, other intense regions, but not as intense as the central region. All right, so the reason you can have diffraction through a single slit is because of Huygens' principle. So we are going to copy this diagram. You have an aperture of size B, and you have two wavelets, X and Y. Where those wavelets meet, you have a first minimum. The midpoint halfway through the slit, you'll have wavelet Y, and at the very upper part of the slit where the wavelet is right against the boundary, that's wavelet X. So the angle between the central reference line, that's the distance from the center of the aperture to the center of the maximum intensity point right here, that angle will be theta. So this is a larger drawing. You can see the distance between x and y, those waves, it's b over 2. And then we have an angle theta labeled. The angle is between the center line that we've drawn, the distance from the center of the aperture to the screen, and this line, this path length of the wavelets y to the screen. So that's the angle theta right there. What we can do is construct a right triangle to make a little more sense of this. So I draw a straight line from wavelet x to the path of the waves coming from position y. This is a 90-degree angle right here. And if we use a small angle approximation where b is sufficiently small and the distance to the screen is sufficiently large, the angle here will match the angle here. So these two angles will be equal. So in this case, we'll have this line right here that I've highlighted, and this is the path difference. That blue line is the path difference between y and x. So you can see y has to travel a longer length to get to this position than x does. Y travels further. So it turns out this path difference here is equal to lambda over 2. Why is that? Because where those two meet, they have a path difference that causes destructive interference. So if we continue to analyze this right triangle, we have theta, we have b over 2, we have a path difference, lambda over 2. This we can use sine theta is equal to the opposite side, lambda over 2, divided by the hypotenuse. This is b over 2. Sine theta is equal to lambda over b, and using the small angle approximation, theta is very, very small, less than 50 degrees or even smaller than that. Then we have sine theta is approximately equal to theta. Make sure your theta is in radians, however. So finally, this is how we have our single slit equation for the location of the first minimum. Theta is in radians, and that's equal to lambda, the wavelength of the coherent light, over b, the width of the slit. So IBO expects you to know the relative intensities of these maxima. So here's a plot of intensity versus the angle. What you see on the screen is the intensity or the diffraction pattern that would be spread across. You would have maximum intensity in the middle, followed by places of darkness and then brightness. With every subsequent maxima, you get a reduction like this. You have I naught, and then this is about I naught over 20, I naught over 50, I naught over 100. And IBO expects you to know the positioning of the minimums. This would be lambda over b, 2 lambda over b, 3 lambda over b. The IBO expects you to know how the shape of the diffraction pattern depends on the ratio of the slit width b to the wavelength lambda. Since theta equals lambda over b, it is easy to see that the bigger b is, the closer together the maximums and minimums will be, the smaller the angle is. Also, having a larger b means more light gets through. A bigger slit, more light gets through, so the more intense the light is. So look at this sketch, make this. You have intensity versus the angle. And this is, again, if you have to have all of it's a monochromatic light source. Okay. So for a larger opening, you have high intensity, but a small angle. The central maximum is narrow. As you increase the size of the opening, you decrease the intensity, and you increase the width of the central maximum. Theta gets larger. Likewise, this even smaller aperture results in decreased intensity and a much wider diffraction pattern. IBO expects you to know how the shape of the diffraction pattern depends on the ratio of the slit width, B, to the wavelength lambda again. So what if we change the wavelength? Since theta equals lambda over B, it should be obvious that the smaller the wavelength is, the smaller the angle is, the closer together the maximums and minimums will be. So here we go. If we have a short wavelength like violet light, you see you have a very narrow pattern. Green light, you get a wider central maximum, wider pattern, and with red light, get less diffraction, you get a much wider angle. So white light will also diffract, but the central max is white and the bands will look rainbow colored, as you can see. All right, practice question number 1. Make sure to put these into the one notebook. Follow along. What type of electromagnetic radiation should be used to produce the first minimum at an angle of 0.272 rad if the slit has a width of 74 centimeters? So we'll use theta equals lambda over B. Solve for lambda. Theta times B equals lambda equal to 0.272 radians times 74 e negative 2 meters. This will give us a wavelength of 0.201 meters. It's pretty large wavelengths, especially compared to visible light, which is in nanometers. And around this scale, these would be microwaves. Number 2, a parallel beam of monochromatic light of wavelength lambda passes through a slit of width B. After passing through the slit, the light is incident on a distant screen. The angular width of the central maximum is, this theta is equal to lambda over B. This tells you the angle from the center of the central maximum to the first minimum. So this tells you if I had an interference pattern. This angle is this angle. That's what this equation tells you. So if you want the width of the entire central maximum, you need to double it. 2 times theta is the width of the central maximum. So in this case, it would be 2 lambda B, 2 lambda over B radians. Question number 3, a beam of coherent light is incident on a single slit of width B. After passing through the slit, the light is incident on a screen at a distance d from the slit. Which of the following changes carried out separately in respect of B and D will result in an increase in width of the first diffraction maximum formed on the screen? So I don't know if you guys have ever shown like a flashlight onto a screen, but if you have a flashlight at home, you should definitely do it. If you're standing really close to the wall, you know that the flashlight is concentrated in a smaller point. But if you stand back against the wall, the pattern of the flashlight against the wall gets larger. So increasing the distance from the slit to the screen increases the separation between the central maximum and the first minimum. It kind of spreads that pattern out. But which of the following, so I know it's going to be increasing the distance d, and get rid of choices C and D, but which of the following will also increase that theta, the width of the diffraction pattern? or the interference pattern. Theta equals lambda over b. Well, if I decrease b, I should be able to increase theta. So the choice here is A. Question number 4. A ray of light with wavelength 600 nanometers passes through a single narrow slit and forms a diffraction pattern on a screen. The angle at which the first diffraction minimum it formed is 2 times 10 to the negative 3 radians. What would be the angle of the first diffraction minimum for the light of wavelength 400 nanometers? So to get this, we need the width of the slit. So we can use theta equals lambda over b, first with our known 600 nanometers and the angle theta, and we'll solve for b. So b is equal to lambda over theta. That is 600 nanometers, e negative 9, divided by 2e negative 3 radians. The width of the slit is 3e negative 4 meters. So the angle for the first diffraction minimum with 400 nanometers, theta is 400 e negative 3 divided by 3e negative 4. Pardon, 400 e negative 9, that's 400 nanometers, e negative 9. 400 nanometers divided by the slit width, the angle would be 1.3 times 10 to the negative 3 radians. All right, thanks for watching. Study well.